In this video, we will discuss this question from Pathfinder Challenge Your Understanding section. So in this question, it is given that there is a very long current carrying cylinder of radius r. Okay, this radius is the full one. Or else I'll just change this to capital R because smaller I have used for a different thing in the solution. So radius of the full cylinder is let's say capital R. And current J is inside the conductor and is uniform over the cross section, and I have assumed that it is flowing inside into the board, and this is the top view. Now we have to find a suitable expression for force of interaction per unit length between two halves obtained by conductor by plane containing the axis of the container. So you just break the cylinder in this way. Okay, this plane has the axis here. Okay, this point we are seeing the top here, that's why axis is line passing through this point, and this full line which I have drawn extends up and down, so that will be the plane. So we have to find force per unit length on the top part by the bottom half, or vice versa. So we'll see how to approach this. The approach that I'm going to do is going to be pretty simple. So I just took a small element of dA area, and length is also there for this. It's going up and down. So it's going outside as well as inside. So it's almost infinite where area of it is dA. Now, by using Ampere's law, we know what is the field value here, magnetic field value. It is just mu naught J bar cross R bar by 2. Okay, this is field inside the formula. So this particular element which I am taking is going to experience this field across its length. Okay, throughout its length, this field will be experienced by that element. So if I write force I L bar cross B bar, so I can clearly write I as J into dA, and I know that J and L have exactly the same direction. So I have just interchanged them. L I have written outside, J I have written inside. So now this dA formula I have substituted the B bar that I got, just like this value here. I got this as the small force on the element, but I want it on the full upper part. So I have to integrate it. Before integrating, I'm using vector triple product for simplifying this part alone. So by using this A bar cross B bar cross C, you can write it as A bar dot C into B minus A bar dot B into C. So I've written the same thing. Here we can tell J bar dot R bar is 0. You can clearly see J bar is pointing into this plane, R bar is in the same plane. So angle between J bar and R bar is 90 degrees. So dot product became 0. So we have minus at J dot J. J dot J, you can simply write it as J square. So I have represented with J square. Now all the constant terms I took outside. Even J square is a constant. So I wrote R bar and dA, which two are the variables. So to get the total force, I'm going to integrate this. So if I integrate, you can clearly see we got R bar dot dA, which is exactly the same thing that we get in center of mass. If you remember, you'll write integration of R bar dm by integration of dm is equal to position of center of mass. And here if you observe, this m can be written as sigma dA. This also is sigma dA. If you take a uniform sheet, sigma gets cancelled, you will be doing the same integration. So the RCOM formula I want to use for that, I have just divided with integration of dA and again multiplied with A. Okay, integration of dA will be A only. So this is your center of mass formula only. That sigma will get cancelled. So this one I have replaced with 4R by 3 pi. So ultimately area value I just substituted pi r square by 2, and this J cap I'm just showing just to tell you that the center of mass will be somewhere here in this direction. The R bar was there, or RCOM bar was there. So force is acting exactly opposite to it. So now to get the force per unit length, this L part alone I took left side. So you got 1 by 3 mu naught J square R cube.